Hello everybody. In this video we'll talk about matrices and how to calculate its eigenvalues and eigenvectors. So without wasting any time, let's get into it. So first of all, what is a matrix? A matrix is a machine, or if I talk in a technical language, it's an operator which operates on a vector and transforms it. So it can transform a vector in 4 different ways or many different ways. 4 of them are: it can rotate a vector, it can stretch that vector, it can compress that vector, or it can flip that vector in an opposite direction. So there are such vectors, a few vectors which only get stretched, compressed and flipped. Those special vectors are called eigenvectors, and the value with which they get stretched, compressed is called the eigenvalue of that vector. So mathematically speaking, if a matrix A acts on any vector x, so A is a matrix, x is my eigenvector, and I get my eigenvector and a number or a scale in front of it, and this is called my eigenvalue of that eigenvector. So eigenvalue is unique to a particular eigenvector. So let's take an example of 2 cross 2 matrix. So this is a 2 cross 2 matrix A. So let's calculate its eigenvalue first. So I have this equation. Let's take lambda x to this side, and this will become 0, and this is 0 not as a number, it's a null matrix. Then if I take my x out, lambda is a number, a scale with which my eigenvector is multiplied with. So if I take x out, in multiplication to lambda, I have an identity matrix, because matrices can be added or subtracted with a matrix only. It cannot be added or subtracted with a number. So the determinant of this matrix gives you the eigenvalues of that matrix. Right, so let's do it. What was my matrix? 2, 1, 1. So let's calculate the determinant of this matrix. Minus lambda, I is identity. So this matrix will become 2, 1, 1, 2, and lambda gets multiplied with every number of identity matrix, and this will become 2 minus lambda, then 1 minus 0 is 1, 1 minus 0 is again 1, and 2 minus lambda is that. And the determinant of this matrix will give me the eigenvalues, and eigenvalues are lambda here. So how to calculate a determinant? Multiply this and subtract with the multiplication of this. So 2 minus lambda multiply with 2 minus lambda, subtract 1 times 1 equals 0. So I have 2 minus lambda square minus 1 equals 0. To open 2 minus lambda square, a square plus b square minus 2ab minus 1 equals 0. This will give me 4 plus lambda square minus 4 lambda minus 1 equals 0. and rearranging this equation would give me this. And to calculate its roots, you can use the quadratic formula as well, and this will give me two roots of this equation, two solution to this equation. One is lambda equal to 1 and another is lambda equal to 3. So the eigenvalues of this matrix are 1 and 3. Now let's calculate the eigenvectors. Just remember this equation. This matrix was, remember this matrix, and we have this, right? So let's take it here. A minus lambda I x equals 0. And A minus lambda I was this equation, which is 2 minus lambda 1 1 2 minus lambda multiplied by x. X is an eigenvector. So x1, its component would be x1, x2, and on the right hand side I have a null matrix. So to calculate first eigenvector corresponding to lambda equals 1, let's substitute 1 in place of lambda in this equation. So I'll get 2 minus 1, 1, 1, 2 minus 1. x1, x2 equals 0 and 0. Now let's multiply these two matrices. 2 minus 1 is 1. Let me simplify it more. Now let's multiply these two matrices. x1 multiplied with 1 would be x1. Then 1 multiplied with x2 would be plus x2. And on right hand side I have equals 0. And from the second equation I'll get the same result, a redundant equation, an extra equation, which is not helping me. So let's look at this equation. It happens, but it's okay. So x1 equals minus x2. So I get x1 equal minus x2. So we have to choose the least number. Let's say x2 is 1. Let's choose the minimum number. If x2 is 1, x1 will be minus 1, and my eigenvector corresponding to lambda equals to 1, let's say x1, would be minus 1, 1. And this is not normalized. In physics, we generally normalize our eigenvectors. That means we find a unique eigenvector to lambda equals 1 eigenvalue. So how do we normalize it? Let's say the coefficient is a times minus 1 square plus a times 1 square should be unity. The sum of these values should be unity. Now it's not unity, it's 2. So that's why I multiplied that with a number a. This is a method to normalize it. So it would be a square plus a square equals 1. 2a square equal 1, and a is 1 over root 2. So the normalized eigenvector would be 1 over root 2 minus 1, 1. So now if you do square and add these numbers, it will give you 1. So that's known as normalization of an eigenvector. So this is an eigenvector corresponding to lambda equals 1. Let's label it lambda 1. Now let's find another eigenvalue was lambda equals 3. Yes. So let's find an eigenvector corresponding to lambda 2 equals 3. Let's find our x2. Now remember, this equation was 2 minus lambda 1, 1, 2 minus lambda, and x2, again let's say x1, x2 are the component of this, let's say y1 and y2 equals 0. Now substitute 3 in place of lambda, would be 2 minus 3 would be minus 1, minus 1. Now let's multiply these two matrices. On the left, we get negative y1, positive y2 equals 0, and we get the similar kind of equation, which is redundant, it's fine. So y1 equals y2 from here. So let's again choose the minimum value. Let's say y2 is 1. So y1 is also 1 because they are equal to each other. So my x2 would be 1, 1. Now this is not complete because if I square the value and add them, it's 2, it's not 1. It has to be unity in order to have a normalized eigenvector. So to normalize it, let's say it has a coefficient a in front of them and square them, plus a times 1, square them should be 1, and then again I'll get 2a square and a would be 1 over root 2. So the normalized eigenvector would be 1 over root 2, 1, 1. So for lambda 2 equals 3, this is my eigenvector. So this is it for this video. I'll see you guys in the next one.